Welcome back, everybody. And to this session on neural networks and setting up our own code for neural networks, and also applying this to the solution of differential equations. And this is a topic which for many of you can actually be very interesting, because every year there is a fraction of you who study numerical differential equations and partial differential equations. There is a course which is actually called numerical partial differential equations. And the last project, project 3, has a path where you can solve differential equations using neural networks. And you can combine that with that specific course where you actually solve differential equations using, for instance, finite element methods or finite difference, which is the most common method which is being used there. So if you're interested in that as a variant for project 3, the material which you will see here is a type of material which you may find useful. And also, since we today are going to mainly go through slides, there's going to be less whiteboard derivations. We are going to discuss a library which is called TensorFlow. So when it comes to project number 3, many of you are often very interested in applying these methods to own data or solving, let's say, differential equations, which is going to be one of the variants. And then you can, if you want to, use these libraries developed by Google or Facebook or whatever, and then benefit perhaps from a speed up, because this is often written hopefully in a better way than the codes we are able to write in just a few weeks. So feel free to use existing libraries when you're dealing with project number 3. And one of those which we are going to look at today is TensorFlow and how we can implement a neural network using TensorFlow. Now, I'm going to repeat some of the things we mentioned at the lab this week, and also bring back some of the elements of the code which we had from last week on setting up a neural network, because that can be useful also when you are setting up your own neural network. And then when we're done with that, we are going to go through the setup of a TensorFlow and how we can use that one to compute a neural network. And when we are done with that, we are going to look at the setup and solution of differential equations. Then, which is I should say, this is something where I'm somewhat biased, but solving differential equation is actually one of these very, very interesting topics as applications of neural networks and deep learning methods. Okay, so the things which we went through during the lab here, there's actually also a video of the lab session if you're interested. So I recorded one of the sessions from this week with many of the small hints and tips. And if you look back at what we did in the lab session, and I just wanted to repeat this and link it up with the codes which we have, is that this XOR gate or OR gate, these simpler cases, these are cases where we can actually set up the derivatives by hand, and we can follow the way the backpropagation algorithm is being implemented. It's also, as we mentioned during the lab sessions, it's useful to set up the feed-forward part just to understand the dimensionalities in the problem. So the system which we have here is a very simple one, where you have 2 inputs, and that defines 2 features. And if you look at the code example which we had last time applied to this specific case, so you see the inputs are bits 0 and 1, and they produce one output, just one specific output. So in terms of a neural network, there are 2 input nodes. And in the exercise here, we're going to have 2 hidden nodes, and then just 1 output node. And the output is a binary output, which means that it's either 0 or 1. And that's one of the simpler cases. And the cost function which you would end up using then is the cost function which we call for the cross entropy. Now, the gates are pretty simple, and your design matrix is exactly the same. for all these cases. The only thing which changes is the output. And in setting up your own code, I mean, it's useful then to have the expressions ready. You make the model with one hidden layer and two hidden nodes. And the sigmoid function is the activation function, which is used throughout. And then you would initialize weights and biases, and you would perform a feed-forward pass. And that is something, the feed-forward pass, those only include you propagating through the network and producing an output. Then the next step is to compare that with the target values and calculate the cost function and the derivative of the cost function at the output layer. And when you've calculated these derivatives of the cost function with respect to the unknown parameters, the weights and the biases, that's when you start propagating backwards and you update the weights and the biases for the hidden layers and all the hidden layers you have, till you reach the first hidden layer. Then you have updated all weights and biases, and then you perform a new feed-forward stage. So in the setup here, if you now look at the code and the case which we had, sorry, in this case I just made up values for the weights, which have to be determined by the training. And we are multiplying a matrix times the weights. So the design matrix is a 4x2 matrix, as you see here. And then you have a 4x2 matrix, which is multiplied by the weights, which connect the input nodes. So you have an x1, this is x1, and this is x2, and you have 4 entries. If you think of this image data set, which we went through last week, we have something like 2,000 inputs, 2,000 images, and each image had 64 pixels. And these 64 pixels define the input nodes. So if you have a larger image, you see immediately that you would get, if you have 100 by 100 pixels, you would need 10,000 input nodes. And everything with a neural network is done through affine transformations, which means that you have matrix multiplications, matrix vector multiplications, which then transform the variables. And clearly, if you have a big image, a neural network is not going to be an efficient way of performing a recognition of images. And the thing is that next week, we are going to look at convolutional neural networks, which is a way to reduce the dimensionality of an image. So what you perform then is a series of multiplications. And through this series of multiplications, you end up with a new matrix. You add the bias, which I just put to 0 and -1 for the hidden layer. So H here stands for the hidden layer, weights and biases. And then this is the input to the activation function. And as we have discussed, there are tons of activation functions. And typically when you run a neural network calculation, you would run through different types of activation functions. This is a ReLU, which simply calculates and compares the values you have here with and find the maximum value with respect to 0. So you see now that these ones are unchanged because they're larger than 0, and the only one which is changes here. Else, you could have taken the sigmoid function, you could have taken a tan-h function, and you could have just gone through the list of all possible activation functions. So typically, when you run a neural network calculation, you would play around with different types of activation functions. And then you would pick the one which gives the best results. And in this specific case, you end up, when you multiply with the output weights, where we put the bias for the output layer to 0. When you perform this, you see that you still have a dimensionality here, which is given by 4x2. So AH is now the output from the hidden layer, and you have X1 has been transformed, and X2 has been transformed. So this is the set of affine transformations which you are performing. And then at the end, we multiply with the last weights, And if the training has been done correctly, we get the XOR gate, which is what we wanted, which has 0, 1, 1, 0. So this is a typical example of what your code would be doing when it goes through the backward and the back propagation and the forward propagation. So I would say one thing you need to think of now is to set up the, when you're setting up the weights, the hidden weights, that will be defined by the number of features you have and the number of hidden neurons. So the number of features are then given by the shape of your design matrix. So if you have 60 features, you would have 60 columns in your design matrix. And that defines the number of features. And that is the number of features which you connect with the hidden nodes in the first layer. So if you have more hidden layers, you would obviously have hidden nodes from the previous layer connecting with the hidden nodes of the next layer. So if you have 100 nodes in each hidden layer, then your matrix, this weight matrix, would be 100 times 100 matrix. Okay, any questions so far? So when the reason why I'm insisting on this is it's so easy to interchange multiplications of matrices and vectors and matrices, and then you may actually get the wrong results. Here you see immediately that in the general case, you will have different, you will not have a square matrix. So you will have often much more data than you have features. So your matrix is not going to be a square matrix. And you would then have a matrix, the input matrix, which is then given by the number of inputs times the number of features you have. And in this case here, what you see now is that when you run set up the weights and the biases, you would just put it to 0.01. You could use a random number. And then we do the same with the output. And the output is given by the output weights contains now the number of neurons and then the number of categories, which in our case, we just have one output node. And in this specific case, we just spit out the probabilities. And the feed-forward pass contains now you setting up the Z of H, where you multiply the design matrix with the weight matrix, as was done up here. So this operation, which you see here. And then you add the biases, which is done here. And then you calculate A of H, the sigmoid, with a sigmoid function in this specific case. And this is what we did here with the ReLU function. So it's still an affine transformation. And then we calculate the output, the input to the output layer. And then finally, the final result is just these probabilities. And if you then run this, you see that you get some numbers. And typically, since this is a sigmoid function, what you would say is that if it's less than 0.5, the output should be 0. And if it's larger than 0.5, it should be 1. So the sigmoid function will just give you a number between 0 and 1. Then you have to tell the output, what you have, what kind of value it should have. When you are comparing it with, let's say, the target values like 0 and 1. Okay, any questions so far? So just the reason why we also have this exercises this week is that if everything works well, you can just ramp it up and then use your code for the full calculations. Now, if you scroll down, I'm not going to repeat everything because this is something which we also discussed during the lab sessions, but you will find a full object-oriented code here, which now contains also the answer to the exercises from last week with the different methods of updating the learning rate. And you will find examples of cost functions here, which you can use in the project. Feel free to use these codes as you want. You will find examples of activation functions. And as I said, there are many, many more than just these ones. And then you will have the final one, which is just the neural network code with a feed forward and a back propagation piece. But let's go back to the examples which we had last week. So I'm just going to scroll down a little bit here because we went through this during the lab sessions. And there is actually an example here where you would run the code for the simple exercises we have this week and next week. So hopefully there is enough for you so that you can get started with writing your own code. So let's now move into the way we are going to set up the code and just quickly remind ourselves about it. The thing which I wanted to dive into is the backpropagation piece, which is perhaps the one which always is a little bit more tricky for people to get started with. So the thing you would do then is collect and pre-process data. You need to define a model and architecture like we did in this simple example. We would choose the cost function and the way we optimize it. We train the model, and then we evaluate the performance of the model on test data. And eventually, we can adjust hyperparameters. So in the first run, you could leave out the hyperparameter lambda and just play around with the learning rate. Now, the results are most sensitive to the learning rate and the hyperparameter lambda. The other parameters which you have tested with AdaGrad and so on, will most likely, but you need to test it, but will most likely be pretty stable when you have 500 to 1,000 epochs. Typically, these are typical numbers. And then you would tune the learning rate and the hyperparameters. So in this case, we have a reduced set of this data set, which is called the MNIST data set, which contains something close to 2,000 handwritten numbers between 0 and 9. And the numbers, as we discussed last time, this is the way they look like. So they're close to 1,800. And then it has, every image has 8 pixels, so which are then transformed into one word with 64 pixels. That's the number of features. So this is your input matrix, the design matrix. And then when you're doing this, you would then set up the feed-forward path. You train and test split. And if we just scroll down here, in this specific case, we have chosen to set up weights and biases, as we did in that previous example I showed you. So the number of features and the number of hidden neurons define the setup of the weights and the biases, and similarly for the output weights and the output biases. Now, in this specific case, you have 10 handwritten numbers, and then we have 10 categories or classes. And then we just have one specific hidden layer with 50 neurons here. And if we just rerun it, then we have the feed-forward pass, where you have to decide what kind of activation function you want to use. And in the case we are using this class with 10 handwritten numbers, types of handwritten numbers, we use the softmax function. And that means that the output from the output layer is now given by this quantity which you see here. And then, as we discussed before, we have a series of matrix and matrix vector multiplications. And the feed-forward pass is exactly the same as before. So nothing changes. And then if we scroll down here, you have an example of the backpropagation piece. So the feed-forward piece is the same here. But then you see that the backpropagation starts with finding the different outputs and probabilities. It finds the error in the output layer. With this is a derivative of the cost function with respect to the output. So Y here is the target. And these probabilities are the numbers you generate in order to recognize whether this is number 0, 1, 2, etc. And then you set up the error for the hidden layers, and then you multiply the numbers you have from the output with the output weights, and then you multiply with the output from the hidden layer, and you have 1 minus A of H here, which is actually the derivative. The quantity you see here is actually the quantity which stems from the derivative of the activation function you have used. And then you have the output weights, output bias for the gradient. And then when you have the expressions for the gradients, for the bias and for the weights, so you have the gradient for the output weights and the output bias and the hidden weights and the hidden bias, then you would simply perform an update here where you now update the terms. And what you see here is just a simple implementation of the gradient descent, where you have a fixed learning rate here, eta. And these are the gradients. So this is just a plain gradient descent implementation. And then obviously you can add stochastic gradient descent to this. You can add ADAM, root mean square propagation, etc., etc. The way the code is set up is in the simplest possible way for plain pedagogical purposes. And then you have the other code, which you saw in the lab sessions, which includes all these different methods. So when you're setting up these codes, it can sometimes be convenient to actually baby step yourself through the different layers and just see that the gradients are giving what you want them to give. And especially for this case with the XOR or OR gate, you have just two inputs, X1 and X2, and one output. And the total number of parameters then is 9. 3 for the output layer and 6 for the hidden layer. And this is something which you can actually control almost by you doing some hand calculations, just to make sure that what the network is doing is exactly what you expect it to do. And just coming back to these cases here, when you now run through the network here, the accuracy is not actually spectacular. And you see now that the accuracy on training data is not actually something you would brag about. And that's when you would typically include these regularization parameters, and you would play around with different learning rates. And if we just run through it, and just to remind you of what we did last week, the score which we look at is the accuracy, where we simply count the number of correct hits divided by the total number of data we have. And in this case here, we just run the network with 100 epochs and a batch size of 100. And then we keep adjusting, and you see now the score is a little bit better. And then we adjust the hyperparameters and run through the network here. And when we're done with that, we would typically make a plot of a heat map and look at the values which give us the optimal description. Actually, my laptop, I don't know why, has been running at a very slow pace lately. So it's been, I don't know what's happening. Okay, let's just wait till it gets through here. Let me see if it just went through here. So it's still performing some runs. I should have run these things before I came here. So one of the things which I wanted to discuss, and actually we showed this last week as well, so maybe there's not a need to rerun it here. But let me see, it's still running actually. Now it should be done. Yeah, I think it's almost done now. Just one more, and then it should be done. Yeah. So when we did this, what we saw is that we had a training accuracy where for a eta parameter, the learning rate of the order of 10 to the minus 3, and 10 to the minus 2, we actually got a pretty good description of the training data with 100% hit in this specific case. And you see also that there is a set of hyperparameters, lambda, from 10 to the minus 5 to 10 to the minus 2 here, which give us a perfect reproduction. And then for our own network, when we look at the application of the model to the test data, it seems that this is the case where we get, in this case here, is the one where we have the best training together with this one. So this would correspond to a learning rate of 10 to the minus 3, and this is 10 to the minus 2. And here we would have a hyperparameter of 10 to the minus 2 and 10 to the minus 1 here. So these are typical calculations which you will run, and then you would typically just pick the value which gives you the best fit to the test data. And that's the one you would present in the report. Any questions so far? So last week, we also went through a scikit-learn implementation, but what I wanted to show you now is more the way you would use TensorFlow. And TensorFlow has an API, which is called Keras. And that's the one we recommend using. Now, you can program in TensorFlow or in PyTorch if you prefer that. So are there many here who have been using PyTorch? Okay, so if you feel familiar with PyTorch, feel free to use that. So have some of you used TensorFlow? No, just one of you. So TensorFlow is Google's, library for doing deep learning. And PyTorch has been Facebook's answer to that, or Meta's answer, as they're called now. And these are libraries which allow you to implement basically all deep learning methods. And these are libraries which are expanding all the time, including many different options. Actually, now they have even libraries on quantum machine learning, which is actually quite interesting. And the way we would recommend, which will save you time, is to use a interface which is called Keras with TensorFlow. So the examples which I'm going to show you here are examples on how you can set up a neural network code using Keras and then run it. And we are going to repeat this when we look at the convolutional neural networks and recurrent neural networks and other methods. And this is something which allows us to, in a quick way, to set up the architecture of the network and run the calculations. And this is a kind of recommended modus, especially when you guys are moving into project number 3. Because in project number 3, many of you would like to apply these methods to own data, which are perhaps relevant for your research or the topic you have in your master thesis or whatever, or just data you want to analyze. And then this is something you can quickly change with a library like TensorFlow with an application like Keras. So let me quickly show you how TensorFlow is actually, after you've installed it, we would typically use Keras. There are some instructions on how to install it in the beginning. So this would be the MNIST data set. So we would still collect the data, and this is a data set which is imported from scikit-learn. And the nice thing is that the functionality of scikit-learn can be fully used together with TensorFlow or PyTorch or any of these modern libraries. So when you've been used to use splitting and test and train, the cross-validation part and everything, these are things which you can interface with TensorFlow and PyTorch as well. So we are just setting up the data set as we did before, nothing special. And we are setting up the train size. So everything which we've been doing before can be reused. And now you can see the way you would set up things here. So in this case, I'm defining 100 epochs, 100 batch size, number of neurons in the first layer to 100, and in the second layer to 50. So one thing which is pretty common to do when you're testing the architecture and your model. So remember now that your model is defined by your architecture. So if you have one hidden layer, the typical thing I would do is to start with a small number of nodes, like 20, 30, and then I increase it. And if I then see that let's say the mean squared error doesn't change much with 100 nodes, I would stop with that. And then I would say that, okay, yeah, with one hidden layer, this is the best result I get. And then I can add the next hidden layer. And then you would keep adding layers till you see that your mean squared error starts increasing in value, because that would be an example of you introducing a higher variance and perhaps you are overfitting. So you would typically start with one hidden layer and play around with a given number of nodes. Then you would move to add a new layer, and I would typically then just keep the same nodes or perhaps change it, make it smaller. But I would normally use the same activation functions throughout, because you have so many activation functions you can play around with that it can easily become a mess. And you won't see the wood for the trees because you have so many options you're playing around with. So I would stay with the same activation functions for the hidden layers. And then just keep in mind that your output layer will often have a different activation function. So if you have this 10, 100 numbers, you would use this function, which is called a softmax, which is tailored to classes beyond 2. So if you use the sigmoid function, if you have a binary case, the sigmoid function is the one you would apply. If you're doing a fitting of a function, like the function you fitted in project 1, what you would do then is that your output would just be your z values which come into the nodes. So you would not have a function, an activation function for a type of regression problem like the one you had in project 1. Another thing with a regression case, which we discussed during the lab session, is that now you're having a neural network, which means that the network is the one which is going to find the best fit to the function. So in project number 1, what you would feed in as a design matrix was a polynomial to a certain degree. If you do that to a neural network, that means you're feeding in a polynomial, then the network will try to fit your data to that polynomial you're feeding in. However, with a neural network, this actually defies the whole idea behind the universal approximation theorem, that the network should find the best representation for you. So that means that if you have a one-dimensional function, you would just feed in the x values as a design matrix, only the x values. And then you have the output, which you want to reproduce, and then the network should find the polynomial for you, or the best representation of that specific function. So this is something when you have a code functioning, try to play around with that and see if you get a better mean squared error if you do a fitting of a function. So you could feed in a third order polynomial as your data points you want to reproduce, and then just have x, the x values as your design matrix, and see if the neural network is able to reproduce that third order polynomial. And then you could try to feed in the design matrix a third order polynomial and see what that gives. And normally the network would actually try to find a better fit than you having the network to fit a third order polynomial in the design matrix. So the design matrix should not contain, in principle, a polynomial approximation if that's what you are trying to do. Because that defies the universal approximation theorem, which says that the network should be able to find the best representation. Okay, so if you now look at what I have here, these are the same things as we did before. We are setting up all the parameters which are needed. And then this is a sequential network. So that means we go layer by layer. And we are simply using Keras, as you can see here, create neural network with Keras. And we set up the first layer, the second layer, and the number of categories. We feed in the eta values and the lambda values. And here you see the way you can set it up. So you have a hidden layer with an activation function. And here we can also add a regularization, or these hyperparameters. And when you see it written like this, with L2, that's an L2 norm in the same way as we did with ridge regression. You can change that to L1 if you want to. And you have a set of hyperparameters lambda, which are defined. And then you will do the same thing with the second hidden layer. And there you have the same, as you see, activation function is exactly the same. And then your output is just now the softmax function. So it's as simple as that. So when we move into project number 3, many of you will find it much more convenient to use a software like or library like TensorFlow. And here you specify also the type of optimizer. So this takes a standard stochastic gradient descent with these parameters which you have here, and then it runs through these different learning rates, which you see here. And then you just run it. And if you then set up the calculations, you're simply setting up in the same way as before. We have this deep neural network where we call the TensorFlow package, the TensorFlow library with the Keras interface. And we do the training, and then we evaluate it, and we set up the scores as before. Now, one of the things when you run this code is that, first of all, in my case, it's actually running pretty slowly. But what you will experience then is that with 2 hidden layers, you are going to get a result which is not as good as the one with a hidden layer, one hidden layer. So adding one extra hidden layer actually doesn't give you a better accuracy. The best accuracy is roughly with 1 hidden layer and 100 nodes. And that gives an accuracy of 98%, which is roughly what humans are able to classify the same data with. So it's not given that you increasing the complexity will give you a better accuracy. And this is something you will have to play around with. Okay, so I'm not going to let this, we're just going to let this run. We have also this breast cancer data. You can take a look at these examples if you want to. But I wanted to say something about the fine-tuning of the parameters, because this is something which is pretty important for us. So as you've seen, there are tons of parameters. Not only can you use any imaginable network topology, but even in a simple feed-forward neural network, you can change the number of layers, the number of neurons, the type of activation function, etc., etc. And the question then is, how do you actually know what combination of hyperparameters is the best for your task? One thing you can use is actually a grid search, if you want to do that, to find the best parameters. In a certain sense, we are doing that by setting up a grid of parameters, and then we would search manually through the results and just pick the one which gives us the best result. Now, these libraries have a ready-made function, which is called grid search. They have random grid searches, etc., which you can use. But typically, the 2 parameters, which are the most important ones, are the learning rate and the hyperparameter lambda. These are the most important parameters. So there is a tool here called Oscar, which implements more complex algorithms to find a good set of hyperparameters. For many problems, you can actually just start with 1 or 2 hidden layers, and it will just be okay. And for this MNIST data set, when you run this case with Keras and TensorFlow, you will actually get an accuracy which is not improved beyond this 98%. This is roughly what you would get when you use 2 hidden layers. And for more complex problems, you would typically ramp up the number of hidden layers until you start overfitting the training set. And very complex tasks, such as large image classification or speech recognition, they have networks which are extremely deep, and they take a lot of time to train. So the question is also which kind of activation functions you should use. And this has been actually a huge debate in the literature. And one of the problems with the sigmoid function is that when your argument goes to -infinity and +infinity, then the sigmoid function flattens out. That means that the derivative of it is going to give you values for these large values of the input, which are close to zero. So if the derivative of the activation function is zero, then you will run into the problem that the training of the network may stop off. So remember now that the training of the network goes through you updating the values of the weights and the biases every time you backpropagate. Whether you're satisfied or not depends on your comparison with the target. So that's when you have performed the feed-forward pass and you produce an output, and that output is compared with the target value. That's where you decide when to stop or not. But when you train the network, you don't want to drive the gradients to zero. And with the sigmoid function, this could accidentally be set to zero, and then the training would stop. So this has often been a problem in neural network calculations. And we have also a similar problem, which is called exploding gradients, which is normally encountered in recurrent neural networks often. These recurrent neural networks, which we will cover in 2 weeks, they have suffered severely from exploding gradients. So there is a paper by Benjo, the author of the textbook, which we use most on deep learning, where they actually addressed this, and this was back in 2010. And what they found, since the sigmoid function was widely used, they found that the sigmoid function was actually the activation function which could lead to these problems, and also the way you initialize the weights. So if you wish to read a little bit more, there's a link in the lecture notes to the article by Benjo, and this actually sparked off a renewed interest in deep learning methods. So when we talk about the deep learning revolution, we're actually talking about time 2010 and later. And after that, there's been an explosion in applications and developments of deep learning methods. So one of the problems actually was with neural networks was simply that people were using the sigmoid function. And this has led to research into different types of activation functions and how to use them. And also what kind of way you initialize the weights. So one of the things they showed then is that the activation function and the initialization schemes actually do play an important role actually. And when you looked at the logistic function, the main problem with that one was the fact that the gradients would vanish. That led to the introduction of this ReLO function, which we discussed earlier. There are many types of functions, one which is this exponential linear unit, which is also used. And you see now that you have additional parameters like this alpha, which needs to be set. So that gives you an additional parameter. The thing you want with the activation functions is that they are simple because you're calling them many times, and that their derivatives are simple. Because when you have a network with millions of parameters, you're actually calculating these activation functions and their derivatives tons of times. So you want them to be simple, you want them normally to be bounded, and you want them to be continuous, and you want them to have derivatives which are easy to calculate and don't introduce too many floating point operations. So these are all concerns you want to include in a discussion of an activation function. And there's always a debate what kind of activation function one should use. It seems that this ELO activation function is better than what's called the leaky ReLO function and variants of it. And this ReLO function performs normally better than a tan hyperbolicus, which again performs better than the logistic function. But which activation function you should use is something you have to play around with. So if runtime performance is an issue, you have many nodes and many hidden layers, then people would normally often use the leaky ReLO over this ELO function because that evaluates an exponential. And exponentials require more floating point operations than just simple additions and multiplications and subtractions. So other things, in most cases, this ReLO function works well. So this is the one which many practitioners tend to recommend. It's a bit faster to compute. And for the output layer, if you use a classification, then the softmax function is normally used if you have more than 2 classes. And for regression task, you can simply use no activation function at all. You just spit out the results of the input. The result is the input to the output layer. I'm not going to go through everything here. I just wanted to mention a technique which is called gradient clipping, which is much used in case of exploding gradients, where you simply just put the gradient back to a smaller value if it's becoming too large. So if we take a top-down view on neural networks before we take a small break, so we should typically divide the data into 2 or 3 parts: a training set, eventually a validation set, and a test set. And then you would typically estimate the optimal error rate, minimize underfitting, and make sure you're not overfitting. These are the typical things you would do, and as you did in project number 1. There are clearly limitations of what we are doing. So take a look at the text here. And one of the limitations is, 1, we are dealing with affine transformations with dense matrices. So the more data you have, the more cycles you will need in order to perform matrix-matrix multiplications. If you have a square matrix, which has dimensionality n times n, a matrix-matrix multiplication with 2 square matrices takes n cubed floating point operations. So that slows down efficiency, clearly. You need label data. These methods are extremely data intensive, and it's also a method which is typically applied to homogeneous data. It doesn't work well if you have heterogeneous data types. And many problems are also not about predictions. And in many cases, we are interested in learning about an underlying distribution. And it's often difficult to actually cast many of these ideas in a supervised learning setting. So just keep in mind, when you deal with these supervised learning methods, neural networks and these deep learning methods are data greedy. They can be slow because they are data greedy, and they require label data. So these are just a little bit about the pros and the cons. I mean, deep learning is extremely powerful, but depending on which method you use, it can have its limitations. And one of the limitations with a neural network is that since you're performing matrix-matrix multiplications, it can quickly reach the limit for what you can do in actual calculations. So after the break, we are going to look at the solution of differential equations with deep learning methods. So today is going to be perhaps a little bit more boring slide day. I will not use the whiteboard much, but I wanted to go through some of these examples with solution of differential equations here, which I think many of you will find useful. In particular, if you're interested in that for project number 3. So I'm going to stop the recording here, or pause it, bring back the recording. So this is one of the many possible applications of deep learning methods to problems in the natural sciences. So one problem which we're going to see next week is about convolutional neural network and image recognition, which is widely used in basically all fields of science. If you're dealing with an experiment with a particle detector, you get patterns in your detector which you want to recognize, and these are just set up as images. And then you can use an image recognition algorithm to figure out what kind of decays you have, just to give you an example. Now, the applications of ordinary differential equations to ordinary differential equations and partial differential equations is a huge and active research field. And this is something which also aligns pretty well for those of you who have been studying numerical differential equations with, let's say, finite difference schemes. So what you will see here is a typical implementation and comparison with a finite difference scheme. Just let me say a little bit about what a finite difference scheme means. So let me bring up the whiteboard here first, and then set up the basic equations which you will often encounter. So a typical example of a problem which you have when you're looking at ordinary differential equations, or ODEs as they're called. So these are normally shortened to ODEs. If you have a first order equation, one of the simplest possible cases is you having a function df of x, the derivative of that one, which is given by some function g of x, and then you have some initial conditions. So you could have an initial condition and that could be something like an f of x equals 0 given by some specific value a. So when we are setting up the neural network, what we are going to do now is actually to feed in the initial condition. And then the way we are going to solve the equations are extremely simple, and you will be surprised by the simplicity of what we are going to do. So what we are going to do now is to set up the difference between the left-hand side and the right-hand side. And we want that difference to be 0, right? Because if that difference is 0, we have the correct solution. And we are going to start with a guess. And that guess needs to have the initial conditions. So you have to fulfill them. And if you're dealing with a partial differential equation, you would also need to bake in boundary conditions. Then what you would do next is to let the wave function or the solution to the problem be represented by a neural network. So your neural network is actually going to be the one which is going to be changed iteration by iteration. And your cost function could be the difference between the left-hand side and the right-hand side squared. And that looks like a mean squared error. This is the simplest possible implementation you can do. And that's what these examples are about. So it's not very difficult. If you have a neural network code, you would set up an ansatz for your solution, which is a neural network. You need to feed in information about initial conditions and boundary conditions. And then when you have that, you're just calculating the difference between the left-hand side and the right-hand side with your starting guess. So let me try to show you some of the standard schemes. So normally, what you would do is obviously to discretize the equation. So this f of x moves over to a discretized equation, which we would write like an x of I. And this is something you would write as an f of I. The same thing happens to x. X is discretized, and this discretization means that you have x going from some x0, some initial value, x1, up to some xn, the final value. So you have n plus 1 points in this case. And the x value, so I goes from 0, 1, 2, up to n. So in total, you have n plus 1 points. You would normally fix the initial value. So this f of x equals 0, for instance, that's something which could be defined by this x0. And we would typically write it like an f of 0 here. So how many of you have studied differential equations numerically? Okay, some of you. You will be surprised how simple the setup is. It's actually everything is based on Taylor expansions around a value. So if we have equally distant points, what we would have then is that this x of I could now be given by some x0 plus I times a delta x, which is a step size. And normally this delta x, if we have it fixed, is given by 1 divided by the number of points which you have. That's a pretty common choice. And now we have made an assumption here where xn is equal to 1, but in principle, we should actually have xn minus x0. If we put x0 to 0 and xn to 1, then this is just 1 divided by n. But this is the way we would typically define the number of integration points or discretization points. And often you will hear this word being called mesh points or grid points, discretization points. I'm going to call them interchangeably either mesh points or grid points. So there are many different words for the same quantity. So this is the way you discretize the equation. And then there are some famous expressions. So you would typically Taylor expand. This f of x around some point. So you would take f of x plus this delta x, or you could take f of x minus delta x. So that means that what you would get then would be, if you Taylor expand now, you would have an f of x plus delta x, and that is equal to an f of x, and then you have plus, and then we get the delta x, and we have the first derivative of x, and evaluated at this point x, obviously. And this goes on and on with higher and higher derivatives. So we would have a delta x squared divided by 2 factorial, the second derivative, and this has higher order terms. Alternatively, you can take x minus delta x, and you can manipulate these Taylor expansions. And there's one famous approximation. If we now look at this f of x plus delta x minus f of x equal, or approximately equal, to delta x times the derivative of f of x, then you can replace the derivative f of x with f of x plus delta x minus f of x divided by delta x. This is an approximation. And you see now that we have left out terms which go like delta x squared. So these are being left out. And when we discretize it, this is going to f derivative is going to be f derivative of I, and that will be given by f of x of I plus delta x minus f of x of I divided by delta x. And this is often written as f of I plus 1 delta x, minus f of I divided by delta x. This is a famous formula, and it's named after a famous mathematician. Does anyone remember what this formula is called for the derivative? There's a famous mathematician which begins with an E as a letter. Yeah? Yeah, Euler's forward formula. Now, what you can do next, you can manipulate the Taylor expansions of x plus delta x and x minus delta x. You can subtract it, or you can add them. And if you add them, you can get an expression for the second derivative. And these are just famous formulas which you will encounter. So this is normally called Euler's forward algorithm, because you are moving delta x one step forward. And you have other formula, like the second derivative. And this is evaluated at a point I. And this is something you can find out as I plus 1. You move one step, plus f of I minus 1, minus 2 times the center point, f of I, divided by delta x squared. This is something you would get by manipulating 2 Taylor expansions, one for x plus delta x and one for x minus delta x. When you add it, you will get this expression because you will cancel all the odd terms. If you subtract these 2 expansions, you will get an expression for the first derivative, which is an improvement to the other one. So this has an error which goes like delta x squared. And there is actually another expression which is better for the first derivative, which is f of I plus 1 minus f of I minus 1 divided by 2 delta x. This is, however, more difficult to use because if you have I equal to 0, then you have a fictitious point with minus 1. So you need, in a way, to start it in a simpler way. And often people start the equations by using Euler's method. And then you can add more advanced derivatives later. So these are famous formula, which you probably have seen. And you will be surprised to see that in many of the partial differential equations packages, these are the formulas which are being used for the derivatives. So this is the finite difference scheme, which we are going to compare with. So this has also an error, which goes like delta x squared. Euler's method, on the other hand, has an error which goes like delta x. So typically what people would try to do then is to make delta x smaller and smaller, and then hopefully get better results. But then you're subtracting numbers which are pretty close to each other, and that can lead to round-off errors, which again can lead to loss of numerical precision. So these are, there's always a trade-off between the way we calculate things and the accuracy and the potentials for loss of, or for round-off errors and loss of numerical precision. So these are the standard recipes which you would typically use. And if you use Euler's method on this differential equation here, d of f dx is equal to some g of x. When you discretize it then, what you would have is f of I plus 1 minus f of I divided by delta x is equal to this g of I. And you see now that you get a recipe where the update f of I plus 1 is equal to f of I plus this delta x times g of I. This is one of the standard methods which you can implement easily. And if you have few points, you can actually do the calculations by hand. And the idea is that the function g is a well-known function. And the other thing which you have is when you want to solve this type of equations is that the initial conditions have to be defined. Because, you know, when you solve a differential equation, you get an equation which contains some constants. And these constants can take any type of value. So just to give you an example of a famous differential equation, suppose you look at this equation here of d of f of the second derivative, and this is given by some, let's say, minus some constant alpha times x. This is a function which has as a solution f of x is given by some a times cosine, and it's going to be given by, if I write it like this, alpha squared times x plus a constant b times a sine of alpha times x. So that's a general solution. And this a and b's, they can take an infinity of values. So that's where you have to specify the initial conditions. So what you need to do then, in order to be able to find a solution, you would typically then say that f at x equals 0, which is normally this f of x0, which we would write as f0, you could require that that one is equal to 0. And then what you see then immediately, it's that sine at x equals 0 is 0. And that means that this f of 0 leads to a having to be 0. And then you can, then you have a solution which will depend only on this parameter b. And then this parameter b, if you take the first derivative of the function, then you can immediately fix that parameter b. So initial conditions are important, and we have to bake them in when we set up a neural network. So in the neural network strategy, the way we are going to set up the solutions to the problem is as follows. So we have a differential equation, d of f dx equal to some function g of x. So what we are going to do then is simply to rewrite this as a d of f dx minus g of x, and we want that one to be equal to 0. So this is the quantity we want to drive to 0. We just take the difference between the left-hand side and the right-hand side. And then we are going to have a measure for whether we are achieving this or not by calculating the squared error of this quantity. So we're actually going to square this quantity, because that will also put emphasis on outliers. So you can now decide, when you look at this function here, you would then typically start with an initial guess. And let's call this h of x, which now has a function h of 0, which obeys initial conditions. Plus, and then we can have a neural network here. NN stands for the neural network, where this is given by x. So we could start with a given guess, where the neural network now is initialized with random values for the weights and the biases. But then we need to have in the solution here, which we're setting up, the ansatz for the solution, we need to have information about the initial conditions. And later, when we are moving into partial differential equations, we need to bake in information about the boundary conditions. Okay? So it's actually pretty straightforward. So what I'm going to do now is just to go back to the slides, because I will repeat a little bit some of this information. And let's just take a look at the slides which we have, and go through some selected examples here. So actually, this information was developed by another person who followed this course, and she has actually actively worked on solution of differential equations. So Christina here is the one who started to develop many of these codes now. And she's now doing her PhD at the Department of Informatics. So we talked about some of these quantities here. So what we would need then would be something which looks like this. So we have a function, which is a trial function, with this h of 1, which allows us now to have the solution to satisfy a set of conditions. And then we would have a function h here, which depends on your x value, and then is a function of the neural network, where p stands for the way we have set up the network. So P is then the model for the network. And we need to ensure then, when we are running the calculation, so the role of this function here is to ensure that the output from this network is 0 when this g of t is evaluated at the value of x, where the given conditions must be satisfied. So let's now take a look at the minimization process. So the way you can do the minimization now, or the optimization process, is to define a cost function, which would then typically depend on this function f and the different functions, which could be derivatives, second derivatives, etc. And you would typically then define this in terms of a function squared. And what we could do then is simply to define this function, which you see here, as a difference between the left-hand side and the right-hand side squared. So you would always start with a guess for the left-hand side and the right-hand side. And with that guess, you calculate the differences between the left-hand side and the right-hand side, and you square it. And then you use that as your cost function here. So to look at a simple example here, this is a function where we have the derivative of g with respect to x, which we know gives us simply the exponential decay here. So we know the solution of that problem. And in this specific case, we have some initial condition g0. And we want the function now to have this information about the initial condition. And we want to reproduce that analytical result. So let's see how we would then set up the function we want to use as a guess here. So if you now look at the function which we would set up, we can now specify some parameters. So we specify this gamma to 2 and G0 to 10. So G0 is the initial condition. And the solution has to respect that. So we would then set up a model where we have a function h1 plus this h2, which depends on your neural network. So when you're setting it up, you need to set up, as we discussed before, you will need to have a certain number of hidden, the type of output you want to produce, etc., etc. So in this case, if you think of the initial condition which you have as a constant g here, so you would now simply say that, you see now that if you have x times the neural network, so this is just a guess on the solution you're making, you know that when x is 0, you have only g0 back, right? So this is one way by which you can start the initial guess. And then what you would do is to calculate the derivative of that function. And you know the left-hand side, then no, the right-hand side of the differential equation. So if this is your ansatz, you would have a G0, which you have to feed in. And then I have an X times the neural network. So your first step then, since you have this function now, you know what the derivative should look like. So this should be given by this gamma times this ansatz you've chosen. And then you calculate the derivative, and then you take the difference. And you square that difference. And you want to drive that difference to 0. So just to go back to the whiteboard here, if you now look at what we had for this specific example, so let me just write it down and then just go back to the whiteboard. So let's just bring it up. So the function in this specific case, which we want now, is the function g, where we have this differential equation. And then we will give a trial gt of x, which is given by a constant plus x multiplied with a neural network of x as input, and p is given now by the architecture of the network, with p could now contain a certain number of hidden layers and a certain number of nodes, activation functions, etc., etc. And then we see immediately that the first iteration, we know that this one is just a constant, which we want to have when gt at x equals 0 is simply equal to g0. And that's the initial condition. So in this specific case, we would just use this g0 to set up the requirement which has to be obeyed when we have x equal to 0. And then we would take the derivative of that one. So the derivative of that one, gt of x, would simply be given by x. So we would have x times the derivative of dn with x plus n of x, or p here. That would be the derivative. And with that one, we have an expression for the left-hand side. So we have this expression here. And then we would simply subtract this one, but now where the g has a subscript t here. And then we can square the difference, because that's going to be the cost function. And then we would take the derivative of that as a cost function at the final output layer. And then we would propagate backward and forward till we reach a solution where the result has converged to a cost function which is equal to 0, or as close to 0 as possible. Okay? So that's the basic recipe. So it's not very, how to say, it doesn't sound intimidating, right? Because when you have a neural network code, this is actually the way you would proceed as soon as you have fixed the initial conditions and set up a trial function. And that trial function we put up here is one which obeys the initial conditions when we have x equal to 0, because then it's just equal to g0. So this is perhaps a very simple function to set up. So let's try to look at the neural network code where we now run this. So the codes here are, the first code is actually a simple implementation. So we are setting up a neural network, and you can see here now, this is basically what we did. So this is a trial function, and this is the terms which we want to drive to 0 when we take the left-hand side minus the right-hand side. And this is the quantity we want to optimize. So the parameters of the network are optimized so that we can minimize this difference. Okay. So we don't need to go through all these details. So what you will see now is an implementation of a neural network, which we have discussed a lot before. So I'm going to use the sigmoid here as an activation function. And the output is just going to be the function itself. So this contains just a repeat of everything we have been discussing before. So it contains the backpropagation algorithm, where this is the cost function. We perform either a plain gradient descent or stochastic gradient descent, etc., etc. And if we now look at the code here, so we have the sigmoid function, which we're going to use. We have the neural network with the number of hidden parameters, the number of output weights, which we want to tune. We have the input here. And then if we go down a little bit, you will see we have the trial function, which we put up here, which is G0, this constant, plus X times the neural network. And then we have the right-hand side of the trial function. And then the cost function is now simply given by the difference between the two functions. This is the error we want to calculate. So the cost function is actually given by the sum over all these errors. And here I'm using automatic differentiation to calculate the derivative of my trial wave function. And then I do the backpropagation. I solve the differential equation. I compare that with the analytical case. So if you have a neural network code, it's pretty easy to actually implement this. And if we now look at the initial cost function, the difference between the left-hand side and the right-hand side is pretty large. But then when I run through the network and I compare with the analytical result, you will actually see that the final difference after a given number of iterations gives a final cost function, which is not exactly 0, but it's still a difference between the analytical result and the final one. So this is the max absolute difference. So you take all the results you have, the discretized integration points, and then you simply obtain a max value, which is 0.04, which is not bad. So this is one potential application. We can move on with more examples. And one of the things you would like to compare that with, you can now have with one input layer and a specific number of hidden layers and one output layer. You can repeat this one now by increasing the number of layers if you want to do that, and see if that improves the result. And you can also compare this one later with the results from finite difference methods. And this is something which we will do here. So again, when you had two hidden layers, you're also getting a result which is actually pretty good. Actually, here the result is not as good as the previous one. So one hidden layer seems to be doing the job. We can look at other types of differential equations. One equation is this for the population growth, where you have a derivative which is given by the function, and then you have a constant a larger than 0 minus this g of t. And in this specific case, you could now, when you set up the initial conditions, you could define that g0 is given by a specific constant, which in this case is 1.2. You set a to 1, and this parameter alpha to 2 here. But now you would try a different, you could still try the same type of initial conditions. So you have this t here multiplied with a network. So this is also something which would fulfill those the solutions here. And the analytical solution is actually this one. This is another case where you have analytical solutions. And if you do that and run the code again, but now with this new function, and later we will compare this to, so in this case, I actually had a pretty better guess. And my network is actually doing pretty well. And the max difference is 0.04. We can then compare that to other methods. And I mentioned to you Euler's method, Euler's forward method. And then this becomes a little bit more interesting because one thing is to compare with analytical solutions, but the other one is to compare to other numerical schemes and see if the neural network can outperform the standard schemes. So Euler's forward method is not the method of choice. It's too simple. It has an error which goes like delta x, but this is a very popular method which is easy to implement. So let's just compare the same type of differential equations where we have both analytical solutions and where we can set up Euler's method as we discussed on the whiteboard. It's exactly the same type of equations. So what we would do then is to implement Euler's forward method, which simply means that we have the new step, t plus delta t, which is given by the previous one, plus delta t times this, the derivative of the function. And the derivative is a known function here, which is this alpha gt times a minus gt. And then you start with initial conditions, you discretize your time step, and then you have a recipe for setting it up. So you would simply iterate from the initial time, t0, to the final time. And that's the way you would update the solution. That's pretty straightforward. So if we run through that and look at the comparison between the two methods, so my neural network with the same number of points, because I'm using the same integration points from x0 to xn, or in this case, t0 to tn. So what you're seeing now is that my neural network is actually outperforming Euler's method. So Euler's method actually gives me a max absolute error, which is 0.01, whereas the network is actually one order of magnitude better. Now, it's a little bit unfair to compare with a method like Euler's method with a finite step size, because Euler's method is not the best one. So you would typically use some Runge-Kutta method to second order or fourth order, which would give you a much better precision. However, when you compare these methods with the same step size, you see now that the neural network actually gives a much better result. So if you want to study these things for the final project, you're very welcome to do so. So you could look at ordinary differential equations, or you could look at partial differential equations. You will find examples of partial differential equation solvers as well here with neural networks. But the basic strategy is this. You have to find a trial function which gives you the initial conditions, and then your solution or your guess contains information about the neural network. So the function you set up as your guess is something which contains the initial conditions and eventually boundary conditions, plus the neural network. And if we just scroll down here, you will find more examples. So here you can actually see the difference between the analytical solution and Euler's method and the neural network here. So the Euler's method is the one in blue here. And you see that Euler's method actually differs a lot. Now, to be fair, in here, we have only 10 values for the function. So delta x is 0.1 between 0 and 1. So that means that we don't have that many points. But clearly, if I were to add more points for the neural network, that would still beat my standard Euler method, which is actually pretty good. So, but normally, neural networks work best when you have problems with high dimensionality, because then many of these methods here really struggle with the number of computational cycles which are needed in order to get a precise answer. Okay, any questions so far? So I have other equations. This is an example of also a differential equation, but this is a differential equation with a 2-point boundary value problem. So this is not an initial value problem. And the way you would solve this one is actually by a slightly different method. The way you would solve this equation is to set it up as a linear algebra problem. And where you would have a matrix which you can invert. So you would have a linear algebra problem which goes like A times X equal to a known vector B. You will normally not invert the matrix because the matrix is going to be a 3-diagonal matrix, and you have efficient ways for doing that. But this is not an initial value problem, it's a boundary value problem. Because you have two boundary values at the domain between 0 and 1 here. So what you would do then is actually to have to implement these two here. And we are going to put up a function f of x, which is 3x plus x squared. So this is a known function, which we have on the right-hand side. For this case, if you look at the conditions, so one way to fulfill these initial conditions is to set up this function. So you see here that if x is 0, then you have 0, obviously, right? If x is equal to 1, this also gives 0 times that one. So there are obviously many different types of initial conditions. So you would have to choose the one which fit the best for the specific case you have. The analytical solution is actually something which is given by a simple function, these exponentials. And then we would simply set up the neural network again, same code, but an initial different type of a solution. And you see now again, the final cost function is 3 times 10 to the minus 3. And if you make a comparison between the analytical solution and the numerical one, they are just basically overlapping for the points which are chosen. So I've only discretized with 10 points between 0 and 1. Now you can solve the same equation by using linear algebra problem. So you can actually, because this is a second derivative now, which you can rewrite using that formula I showed you. This is one of the famous formula for the second derivative, the approximation to it. And then you actually end up with a linear algebra scheme. So I'm not going into those details. So this is more for the differential equation solvers experts. But if you're interested, I can say a little bit more about it. But there's a standard way of rewriting such equations in terms of linear algebra problems. So you could invert the matrix, but that's not very efficient because the matrix is so-called 3-diagonal. So it has only constants along the diagonal and along the two non-diagonals below the diagonal and above. And this is a problem which you can easily actually solve by an algorithm which is called Thomas algorithm. But we are going to conclude now by simply comparing our neural network with the best numerical method. So you see now that using AutoGrad and our neural network, we actually have a max absolute value of 10 to the minus 4. Whereas the best result I get with 10 integration points with my numerical scheme, finite difference scheme, is actually 10 to the minus 3. And again, you can see now that the numerical scheme with using the so-called Thomas algorithm and the linear algebra-based recipe gives us a result which is inferior to the neural network. But if you now run through some of the examples, and when you come to the diffusion equation, you will then see that my neural network solver needs improvements because I'm just running it still with just one hidden layer. So there are many improvements you can make here, but even these simple cases show you the strength of using neural networks. And the cost function now is just a difference between the left-hand side and the right-hand side square. And this is the quantity we optimize. Does that sound okay? So it's conceptually, it's not very difficult, right? And when you have the machinery with a neural network code, and you know how to calculate derivatives, then this is just a piece of cake. It's almost a walk in the park to solve this type of problems. And there you see the benefit of AutoGrad, because without AutoGrad, you would have to set up the gradients for every new function you plug in. With AutoGrad, you just calculate the derivatives by using AutoGrad with automatic differentiation. So you see the benefit of having a general algorithm, even if that may require more floating point operations than you setting up the analytical derivative. But then you have to, when we talk about time, and this is something we discussed at the lab, the total time is not the runtime. Even if your handwritten gradient may outperform AutoGrad, because AutoGrad has overhead, it calls functions, but the total time is the total development time plus runtime. So if it takes you a month to find the analytical derivative and program them, and it takes you a day to write in the function you want to calculate, like we did here, even less than a day, and if AutoGrad just takes some few minutes more, then a day plus some few minutes more is much, much better than a month plus some minutes. So the total time is development time and runtime. And that's the time which is interesting. And you see how easy now it is with the automatic differentiation to just change function you want to calculate. So if this is of interest, and you're taking courses in numerical methods for differential equations or numerical mathematics, or some of you may be taking computational physics, and you want to combine the two, feel free to do that for project free. Many people have done that every year. Any questions? We take a break, and you guys are going to suffer with project 2 over the weekend, then thereafter, and hopefully there is enough help. Okay, guys, let's take a small break then.